Okay, so welcome back to another video. So in today's video, suppose that we are given the following. So we have a function I and then our input a. So I of a is equal to the infinite series with our starting index n is equal to a of -1 quantity to the power n multiplied by the integral from 0 to 1 of 1 minus x to the power n minus 1 divided by ln of x multiplied by the infinite sum of x to the power n to the power k dx. And the question we are being asked to compute is to find the value of I sub 2 and plus I sub 3. So basically we put 2 for a and 2 for 3, then find the sums together. I know that the function may look a little complex and there's like a lot to deal with since we have an integral and 2 infinite sums we're working with. But if we actually just play around with rewriting the expression more and then using our definitions of some properties pertaining with the sums and the integrals itself, then it's not going to be a big issue at all. So anyway, how about we start off by first let's actually take a look at the integral from 0 to 1, and then multiply with that sum, and let's actually rewrite that expression. So let's see, what I'll write is find another expression for this integral in particular. So integral 0 to 1 of 1 minus x to the power n minus 1 divided by ln of x multiplied by our infinite sum starting index k is equal to 0 of x to the power n to the power k dx. Okay, so pay attention that as 0 is less than x, which is less than 1, because that's our integration we're trying to integrate in between, but also and for n is greater than or equal to 2, simply because we're starting with our a is equal to 2, and that n is the lower index in this case, and anything upper than that, so that's what we're going to take this account for. So let's notice that this infinite sum x to the power n to the power k, it converges uniformly. So I'll just write this, I'll just draw this little arrow here to denote converges, and then uniformly. I'll just put uniform just to shorten it. So what this means, what we can do is, because of this, we can actually interchange and interchange our order of integration and our summation. So this means this is actually going to be equal to, so this arrow just denotes rewriting this expression, just interchanging. So we have that this is our infinite series, k is equal to 0 of the integral 0 to 1 of 1 minus x to the power n minus 1 divided by ln of x, and then multiplied by x to the power n to the power k dx. Okay, so I just interchange our order of integration and summation, so that's nice. Now, here's the next step. Okay, so the next step is, let's suppose that I'll say let x to the power n to the power k equals x to the power b. Okay, so then let's actually, then I'll just say then define, and then I'm gonna just write this in orange, so we're defining in particular. So I'll call this function, so it's just the same function I, but we're defining it in terms of our input as b. So this means capital Y b is equal to the, so it's just the same thing as top as before, the infinite sum k equals 0, and the integral 0 1 1 minus x to the power n minus 1 divided by ln of x, and then replace the x to the power n to the power k with x b dx. Okay, now with that, we can actually use Feynman's trick or the Leibniz's integral rule to actually take the derivative of the function. So this means this is capital I prime of b is equal to the derivative to respect to b of the same thing, integral 0 1, then 1 minus x to the power n minus 1 divided by ln of x, then x to the power b dx. Okay, then using partial derivatives, I can actually just move this the derivative into the inside of our inside of the integrand. So really it's just taking the partial derivative in this sense. So let's see, this is infinite sum k is equal to 0, and then our integral is 0 to 1 of del b of our derivative, or of our integrand. 1, then ln of x, then x to the b d, or dx. But this is not that difficult to show because you can see that clearly we're taking the derivative in respect to b of this integrand, but since there's only a b associated with the x to the power b, as you know, this is taking the logarithmic derivative, so it's just the derivative of x to the power b simply when x is just a constant, b is a dependent variable. It's just x to the power b multiplied by ln of x. So we'll just substitute that back in. Then we get that this is k is equal to 0, and then integral 0 to 1 of 1 minus x to the power 1 ln of x, then multiplied by ln of x, and then multiplied by x to the power b, and dx. Okay, and then you can see that the ln of x's just cancel each other out, so we just left with 1 minus x and 1 minus x to the power n minus 1, and then multiplied by x to the power b dx. Distribute that. K is equal to 0, 0 to 1. Let's see, if I distribute this, I get this is x to the power b, and then minus x to the power b plus n minus 1 dx. Okay, and I'll just say so far that's actually just equal to capital I prime of b. So we can keep going and just take the definite integral of this expression over here. And that's not hard to show, so I'll just write this separately. So this is 0 to 1 xb minus xb plus n minus 1 dx. Simply just take the derivative, use the power, or take the integral, then this is just using the power rule, so this is just let's say x to the b plus 1 divided by b plus 1, and minus x to the power b plus n divided by b plus n, and then that's from 0 to 1. But you can clearly see that if you plug 0, the whole thing becomes 0, and then x equals 1, any power raised from the base 1 is just always going to be equal to 1, so this is just 1 divided by b plus 1 minus 1 divided by b plus n. Now, going back to here, we established that capital I prime of b is equal to this infinite series. K is equal to 0 of 1 over b plus 1 minus 1 over b plus n. And now next thing we want to do is let's actually take the integral to both sides. So to get our capital I function, let's see, take the indefinite integral. So this will be in respect to b, and let's see, the sum k is equal to 0, 1 plus 1 minus 1 divided by b plus n db. Now you can clearly see that this is actually, we're actually taking the indefinite integral. All right, so that means we have that capital I of b is equal to, so it's the sum, the infinite sum, k is equal to 0 of the natural log of b plus 1, and then minus the natural log of b plus n, and then plus c, since this is an indefinite integral. But I can rewrite this a little further because we have our two difference of natural logs, so I'm just using our rules of natural logs. So simply this is just under division inside that natural log input. So this is the natural log of b plus 1 divided by b plus n, and then plus c. Let me underline this in black just to establish what we have so far. So we have the left hand side so far is I of b is equal to this. Next thing we want to do, I can actually rewrite things a little further from here rather. So what I can do is, right here should be good space. So I'll actually add and subtract n. So going back to here, infinite sum Alright, so I'll add and subtract an n. So this is b plus n, then minus n plus 1, then divided by b plus n plus c. Okay, and then I can actually just reduce this a little further. So let's see, k is equal to 0. ln of, so b plus n divided by b plus n, so that's just 1. I'll factor out the negative, so this is minus and then n minus b plus n plus c. Okay, so now the next thing we want to do is we want to find what our constant c is. Okay, so to do this, let me go back to the red marker. To find c, let's actually consider the following. So let me first just write the step to find c. Then let's consider the following. Let's actually take the limit as b approaches infinity of capital I of b. Okay, so that would also mean I had to take the limit of the other side too. So that means I would take the limit from over here. So that means the limit as b approaches infinity of our infinite sum. Say this is k equals 0 of 0, 1 of 1 minus x to the power n minus 1 divided by ln of x, and then x to the power b dx. But you can clearly see that, so I'll just write note that the limit as b approaches infinity of x to the power b is actually equal to 0, since we're looking at our interval from 0, between 0 to 1, so 0 is less than x, which is less than 1. So simply, I'll just put back the 0 over here. That means, write this. This is just simply just equal to 0. So now that means going back from here, we said that the limit was equal to this. So let's see, that means the limit has x. I'll just write what we have. That means the limit as b approaches 0 of our infinite sum, ln of 1 minus n minus 1 divided by b plus n plus c is equal to 0. But we already showed that these two are equivalent. These two are equivalent to each other. These two equations. So that means that they have to. It has to equal 0, and so therefore we're left with that c is just equal to 0. So let me put this. This is just 0. So we get that just c is equal to 0. This just reiterate one more time, because this equals 0 simply because if we rewrote this and this is what we get, then we can actually just take the limit as b approaches infinity. This is just infinity is, let me see, 1 over infinity is just 0, so we're left with ln of 1, which is just 0, and then we're just left with c on the side. So we can just set these two, basically we set that this is the limit as b approaches infinity of I b is equal to 0, so it's the extreme right hand side is setting to, we set that, equate that to our evaluated or rewritten expression from here. So set these two equal to each other, find c, we get that c is equal to 0. So that means just rewriting things again. So let's see, our sum, and then the interval from 0 to 1 of 1 minus x to the power n minus 1 divided by ln of x, and then x to the b dx is simply just from this series up here, 0, and ln of 1 minus n minus 1 divided by b plus n. Or rather, just go back undoing the rewritten input, we just go back to b plus 1 divided by b plus n. So now putting back our undoing our substitution, we set that x to the power n to the k equals x to the power b. So how about we plug everything back for b. So if I just take the natural log of both sides, use the rules, we get that putting back, let's see, we get that this is b is just equal to n to the power k. So we just put everything back for b and back for n to the power k. Then we have, let's just rewrite the same thing again, 1 minus x to the power n divided by, or minus 1, and then ln of x, then x to the n to the power k dx. Simply we just set that equal to the sum k is equal to 0 of the natural log of n to the k plus 1 and then n to the k plus n. But which is equal to, so I can actually just factor out the n from here. So let's see, k is equal to 0 and then the natural log of. So this is numerator stays the same, but I factor out the n from the denominator, so we get that this is n to the power k minus 1 and then plus 1. So, well, I can rewrite this even further just using natural logs. We're going to rewrite this a little differently. So this is k to the 0, then natural log of n to the power k plus 1, then divided by n to the power k minus 1 plus 1, and then subtract that from ln of n, or rather just write it as the series again a second time, so then the natural log of n. Okay, simply what I did was I just used natural log properties since this is the denominator, so we use that as a difference of natural logs, and I just moved that outside separately so it has its own little series under that subtraction. And so now, so this term will still stay the same. However, on this side here, notice that if I were to take the if I take the summation of all those ln of n's for each k, we get that this is actually just adding quantities of the natural log of n. But if we take if we actually use our natural log rules, we're actually using the products of those inputs. So it's basically the natural log of n times n times n times n many times. So this actually means I can write this in a limit. So the limit, I'll actually denote this new variable. I'll just call this chi, which just looks like a squiggly x, and I'll approach that to infinity of the natural log of n to the power chi. But it approaches infinity, but we know that intuitively if I add plus 1 into here to the degree, it's going to maintain the same. But in a sense, but if I add a degree 1, we're just manipulating things a little bit more. That way, furthermore, like later, when we're trying to like rewrite some things, it's actually going to come out very nice. So that's what I did. I just rewrote the degree from here. And we're going to manipulate some things later eventually. That's actually going to come out nice and smooth once you see. Going back to the orange, there's something that I want to write up here. So let's see. Note. So let's note that the let's see, the series from here, which is what k is equal to 0 natural log of n to the power k plus 1 and divided by n to the power k minus 1 plus 1. Simply using our logarithmic rules and continuity, I can actually rewrite this as the natural log of the product series. So this is k equals 0, and then this is let's see, this is just same thing, the same input, so it's n to the power k plus, it's just n to the power k and then plus 1 divided by n to the k minus 1 and then plus 1. Alright, cool. That's my continuity, so I can actually rewrite this expression from here using this rule here. But notice that the natural log of our product series k is equal to 0 and then k plus 1 divided by n to the k minus 1 plus 1. If I were to expand this series out, then I'll just write this in limits. So the limit as chi approaches infinity of, so let's see, let's start our index. Let's see, this is n0 plus 1, and then plug 0 here, so it's n to the negative 1, which is just 1 over n, and then plus 1, and then if I plug 1, so it's just n plus 1, and then let's see, n to the 1, so it's 0, then that's basically just n to the 0 plus 1, then n plus 1, so n squared, and then n plus 1 here. Okay, keep going, so on and so forth. Then we get that, we plug, this is just n to the power k plus 1, and then n to the k minus 1, or rather this is supposed to be the Greek symbol chi, so let's fix this. So far we just expanded this out, but you can clearly see that you're gonna get some terms that cancel out. So n0 plus 1, those cancel, this cancel, it's like diagonal cancellation. However, now with that means the only thing you're left with is the limit as chi approaches infinity of n to the chi plus 1, then divided by over here, so divided by 1 divided by n plus 1. Okay, so I can actually just replace what we evaluated here from here. So I can just replace what we expanded this series out from here. So this means, let's see, the series, infinite series, k is equal to 0 of the natural log of n to the power k plus 1 divided by n to the power k minus 1 plus 1. This is just simply just the limit as chi approaches infinity of n to the power chi plus 1, and then divided by 1 divided by n plus 1. Or, well, actually this is supposed to be the natural log, so let me see, let me just rewrite this back here for a second. Over here, that's natural log, so this is the natural log of n chi, yeah, or rather, yeah, that's where it is. It's 1, then 1 over n plus 1. Okay, just replace this back with the natural log. Yep, so just rewrite what we have over here, and then back with just that expansion back from here. Okay, let's reiterate some things. So starting from here, the summation of the natural log was k is equal to 0, and then the natural log of n to the power k plus 1, then multiplied by, or divided by n, multiplied by n to the power k minus 1 plus 1. So far we said that this is just a limit as chi approaches infinity of the natural log of n to the power chi plus 1, or yeah, plus 1 is supposed to be down here, not with the exponent. Then divided by 1 divided by n plus 1, and then we subtract that with this limit, so the limit as chi approaches infinity of the natural log of n to the power chi plus 1. Okay, so now what I'll do here is that rewriting some things. So I'll just multiply and divide in n. So let's see, multiply, divide in n. So this means we get that this is n chi plus 1, and then plus n, and then multiplying n over here. So I'll get that this is a n plus 1. Okay. And then we subtract that from the natural log of n to the power chi plus 1. And rewrite this even further. What I'll do is I'm actually going to interchange these terms. So because you can do this because this is under both the natural log rules. So this is still under the division symbol of the input of the natural log, but this time I'll actually move the n plus 1 outside or back to this term, and then move the n chi plus 1 back into this term. And you'll see why I do this like in a couple steps later, why this comes out nice. So just rewrite. So this is the natural log of n to the power chi plus 1 plus n, and then chi plus 1, then minus ln of n plus 1. And then if I rewrite this even further, then we can actually reduce this. So we get the natural log of, so this is actually just 1, and then plus, so let's see, they both share the same base of n, so this n chi times n, so the n's cancel from both the top and bottom. So we get that this is just 1 divided by n to the power chi, and then minus ln of n plus 1. Now we want to note that as n is actually greater than or equal to 2, then when we take the limit, so we take the limit as chi approaches infinity of 1 divided by n to the power chi is actually simply just going to equal 0. Okay, so we'll just use this to replace some terms here. So going back to here, we get that this is just see the limit chi approaches infinity. So we get that this is just ln of 1 plus 0 from here, so this is just ln of 1, then minus ln of n plus 1. Then you know that ln of 1 is just 0, and then you just get that we just end up with negative ln of n plus 1. So now to reiterate, and I'll just write this to the side, and I'll underline this in black later. So basically to come to that conclusion, we see that this is actually the infinite series k is equal to 0 of the interval 0 to 1 of 1 minus x to the power n minus 1 divided by ln of x multiplied by x to the power n to the power k dx is equal to the negative natural log of n plus 1 right over here. Okay, so now we focus with just the interval and the summation here. Now let's actually just plug it back to here. So let's see. We have the infinite series n is equal to a of where is it? Negative 1 power n, and then we multiply this by the negative natural log of n plus 1. How about I write it like this? We'll just rewrite the original series, infinite series and interval that we're given. So going back 0, 1, 1 minus x to the power n minus 1 divided by ln of x, and then x to the power n to the power k dx, or oops, this is supposed to be with the series, associated with the series. Series k is equal to 0, and then x and k dx. This is just a of, let's see, negative 1. So we see that this is a negative 1 multiplied ln plus ln of n plus a. There's a base negative 1, so I'll actually add 1 more to this degree, so this will be an n plus 1, and then multiply by the natural log of n plus 1. So far we had that's defined as capital I sub a. Just right so far. Just underline this in black again. That's the reiteration we're still dealing with. Okay, and we're not too far from achieving our goal. So now next day, because we're being asked to evaluate I sub 2 and I plus I sub 2, I of 2 and I of 3. So let's actually compute those using what we evaluated or express. So let's actually go back to the red. So now let's calculate our I of 2. So I of 2 is equal to, so that means our starting index has to be n is equal to 2. All right. So we get that, let's see, so 2, so this is negative 1, and then, so negative ln of 3 plus ln of 4, then minus, let's see, 2, 3, 4, then minus ln of 5, and plus dot dot dot. We can actually rewrite this using our rules of natural log. So it's the natural log of, let's see, so this is 1 over 3, then multiply by, this is 4 divided by 5, and then multiply by 6 divided by 7. But I can actually rewrite this a little further. So since there's a 1i, I can actually just move those terms to the left by 1. So we get that this is the natural log of, let's see, 4 over 3, 6 over 5, then 8 over 7. And then we can see that this is actually just a product series. So this is equal to the natural log of, I think I got room for this, the natural log of the product series starting from k is equal to 0 of 2 to the power k divided by 2 to the k, or rather this is supposed to start from 1, or no, 2. This is supposed to start from 2. A product series. Let's see, our product series, k is equal to 2 of 2 times k divided by 2k minus 1. Okay, so let me just go back. So underline I sub 2 is equal to this product series over here. Okay, good. So now let's actually evaluate I of 3. So I of 3 is equal to, so now our starting index will be at 3. So let's say this is positive, ln of 4 minus ln of 5, then plus ln of 6, and then so on and so forth. That's simply, we can write this as the natural log of, let's see, 4 divided by 5 multiplied by 6 divided by 7. You can see the signs just kind of alternate, and then multiplied by 8 divided by 9. And then you can see that this is actually rewriting another product series, the natural log of the product series of, so our indexes still can be defined as k is equal to 2 of 2 to the power k, and then this time this will be 2 times k plus 1. I think I said 2 to the power k, I meant to say 2 times k. Okay, so now underline what we have evaluated for I of 3. Okay, so now the next thing to do is actually just combine the sums together. So let's see, we have I2 plus I3, which is equal to the natural log of the product series. So let's see, k is equal to 2 of 2k minus 1, then plus ln of the product series, k is equal to 2 of 2 times k divided by 2k plus 1. And using those natural logs, we can actually just combine using the product. So that way we get that this is just the natural log of the product series. K is equal to 2 of, let's see, this is 4k squared divided by, and then I'm not gonna multiply the 2 together, I'll just keep it together as 2 binomial factors. 2k plus 1 and then 2k minus 1. Okay, good. So far so good, that's what we have. Now, let's actually recall a little definition that's going to help us make things easier. This is known as the Wallace product. So, definition of the formula, Wallace product is defined as follow, which is the product, the infinite product at k is equal to 1 of 4k squared divided by 2k plus 1 multiplied by 2k minus 1 is simply just equal to pi divided by 2. So we have that definition. So now the rest is going to be a piece of cake from here. So let's see. That means, how about I set it like this? So the infinite product, k is equal to 1, 4k squared divided by 2k plus 1 multiplied by 2k minus 1 is simply equal to, so because our starting index is equal to 2, so we have to evaluate what is evaluated at k is equal to 1. So when we plug k is equal to 1, we get that this is just 4. And then let's see, plug 1 into here, so let's see. 2 plus 1 is 3, and then over here is 2 minus 1 is 1, so this is just 4 over 3 multiplied by the product series. We started our index k is equal to 2 just from over here. Let's see, 4k squared, then divided by 2k plus 1, then 2k minus 1. Okay? And then we said that this was equal to pi, so the pi squared divided by 2. So we said that the left-hand side is equal to the right-hand side. So in order to adjust this, to get just the product series itself, what we're looking for, this input of that natural log, I can just divide a 4 over 3 to both sides. So that way I get that the product series of starting from k is equal to 2, 4k squared divided by 2k plus 1, then 2k minus 1 is simply just equal to, let's see, so for the reciprocal, so this is 3 pi, then 3 pi divided by 8. Okay, and we're just about done. We just put this back to the natural log to get our sum I2 plus I3. So therefore, in conclusion, I2 plus I3 is simply just equal to the natural log of 3 pi divided by 8. And there we have it. All in this red box. So, right then. Yeah, that's pretty cool if you ask me.